Thank you very much, and hello, Porto. So today I'm going to talk about developer environments, and I'm just going to jump straight in because we've got quite a lot to cover in 30 minutes. I want you to imagine you're working on a Django site locally with run server. You've got a bug to solve and you're deep into debugging your Django view. You're in that iteration phase where you want to be constantly making small code changes to get to the root of the issue. And so you have to change, so you're going to make a change to add a trusty old print line. And you hit save. And then you wait. And you wait a little bit more. And 18 long seconds pass by. By 16 seconds, I'm mildly miffed. By 12 seconds, I'm counting how many times that Chrome animation is looped. By 8 seconds, I'm seriously questioning my life choices. And by 4 seconds, I've given up and I'm reading something else, to be honest. So, how did we get here? This was our situation on a daily basis. Instead of making 5 to 10 edits a minute on a Django code base, you reduce to 2 if you're lucky, and it's a super excruciating level of frustration for everyone. Makes day-to-day development super annoying. So, how did we get here? Cross-platform developer tooling. And to understand why that matters, we first need to understand why we'd even need it in the first place. Without any help from developer tooling on a cross-platform team, and by cross-platform I mean across OS, Windows, Mac, Linux, you'll see install issues due to different hardware, operating systems, previous installs and configuration, severe version mismatch, across your colleagues' environments, or worse, production. And if you're in a leadership position such as I am, you're constantly needing to troubleshoot others' issues. And I'll go as far as saying that a decent developer setup is a prerequisite to hiring juniors, because otherwise you're deliberately setting them up to fail, and it's just not fair. And so historically, we and any other cross-platform team have looked to developer tooling to help us out with this. A nostalgic slide for anyone that's been a developer for probably more than 10, 15 years. There were the before times, like pre-2010. We don't speak about the before times, but it's safe to say many joyless hours were wasted setting up developer environments with custom scripts, or worse, nothing. Then in 2010, Mitchell Hashimoto, CEO of what became HashiCorp, came along and gave us Vagrant, which made working with VirtualBox VMs in a headless fashion via the command line much easier. It had its drawbacks though, and when Fig, which was later renamed to Docker-compose when they bought it, came along in 2014, it wasn't long before I switched to it for all my projects, and so did a lot of our industry. For those of you that don't know Docker-compose, you can think of it as a tool for starting various Docker images with their own file system, and then optionally mounting your host file system so you can make changes live, and they'll update in the actual Docker image without having to do a rebuild. On Linux systems, this occurs natively due to Linux container support, but on Mac, it effectively starts a VM known as the hypervisor. And this means that the host file system must interact with the virtual file system, which is key to understanding where most of our problems lie. And so this is our actual stack for languages. We've got Python, JavaScript, TypeScript, and then a whole bunch of services that back the product. As an industry, we like to call monoliths simple, and they tend to be when compared to microservices, but that doesn't mean that setting them up on a per machine basis isn't a complete chore. You end up doing a lot of puppeteering to bring things up. For example, can you imagine bringing up all these services one by one just to get your development environment going? Nope. So to give a little bit more background, we're Unigena.com, we're a freelancer market. We have about 10,000 files in our repository that we need to care about for the purposes of this talk. It's about 2.6 million lines of code, most of it JavaScript. This isn't a boast, because this isn't even a big repository, but it plays into where we're going. And so that brings us into the Docker-compose stack we had. We were running the Python container and all services within the Docker-compose stack, and the front-end build sits outside it deliberately, because we never once managed to successfully isolate the front-end build without serious performance issues. And so when the slowdowns of the back-end container progressively got worse and worse, it was obvious where to look. And a simple experiment confirmed our thoughts. We simply ran the Python container without the file mount, and changes such as like reloading the run server end up happening really quickly. So, how do we solve it? We know the issue is related to the file sync, as the Python container with no mounts just runs fine. But to do local development, we need the mount. And we need the mount because otherwise you're going to be rebuilding the Docker images after every change you make, which is just not scalable at all. We also know it's related to the size of the repo, and we know we can't just delete our repo. And we know we don't want to go backwards to a world where we spend hours every week debugging various environment issues and versioning problems. So, what are we working with? What are we trying to improve? Our run server reload was about 15 to 18 seconds on an M1 MacBook Air. Any management command would just sit there for about 10 to 15 seconds before it even did anything. And I never got to the bottom of truly why this was, but to reset the test database via PyTest, it took 14 to 15 minutes, which is insane. Ahead of myself. So, the goal for us is at least a 50% reduction as part of this project to get us back to reasonable but not terrible levels. And we had a look at all the way forwards. We went back to first principles to really see all the options available to us. And the first one is obviously there's always the option of doing absolutely nothing. Docker have shown a decent amount of interest in fixing the issues with their hypervisor on macOS. But the situation is really gnarly. This is the main GitHub issue about the problem. The line on the right is actually only half the thread, but if I made it any longer, it wouldn't even appear on the screen. So this is opened in March 2020, has about 700 comments. It's the kind of GitHub thread you never want to find when Googling for a quick solution to your problem. But they have tried hard. They have tried hard. So recently they switched their plans from integrating Mutagen, which I'll get to then GRP Fuse, and then again earlier this year with the experimental VirtuoFS. But none of them helped us, unfortunately. And the introduction of M1 chips and us getting MacBooks, despite I asked my boss for new laptops, he gave them to us. The situation ended up worse. Serious egg on face moment. Here we go. So option 2, and I'm sure a lot of you on Linux are screaming, why don't you just use Linux? It's not a realistic solution for our company to use. The entire company uses MacBooks. All of our IT infrastructure is Apple, security policies, security questionnaires, like the list is endless. Everything refers to Apple. And I can't change that. I'm just one man. Being a freelancer market, we also work with many freelancers, and they bring their own kit, and they use Windows, and some of them use Linux and get the platform working fine. So yeah, we need cross-platform support, basically. And so the third option is to try and speed up the sync. We know that when we don't mount the file, it's fine. So what if we can find a way to improve the performance of the sync between the hypervisor and the host machine? And we did it actually for a little bit. There's a project called Mutagen, and you can think of this like a bidirectional rsync with a low latency file watcher. It's written by one guy, as far as I'm concerned. Don't have his name here, unfortunately. It was actually designed to sync between your local machine and remote locations, whether that be Docker or otherwise. Perhaps you're doing development in the cloud and you want to sync your local file system. But there is a handy solution that specifically works with Compose by creating a volume and using the Mutagen protocol to sync that with your host machine instead. But we used it, and it was in alpha. It did help for us for a long period. But then we had issues changing branches. We'd get stale file state, especially on large branch changes. And random bits of code appearing in your PRs is not something you ever want to deal with on a daily basis, so we had to get rid of it. Having said that, it's moved on a lot since we used it a year ago, and if you are having Docker speed issues on Mac or Windows, give this a go before you do anything else in this talk. So the fourth option And the one we're going to talk about the most today is going native. And so by native, I mean running the Python project on the actual macOS file system. And everything stopping us doing this is all the problems I've discussed already, due to you need a reproducible environment for developers. And the fifth option, which this talk was going to be more about, but it's not going to fit in the time, is to go fully remote. So take development to the cloud and base the cloud development with Linux. There's a lot of services doing this, and I think it's the future, but we'll get to that. So yeah, there we were. We had 5 choices, 3 were dead ends, 2 remained, and that is when Nix entered the chat. So it changed everything for us in terms of local development, and from my perspective, potentially much further afield too, once we spend more time with it. So I was first introduced to it by Replit, which is like an online cloud development environment. In about 2018, they switched to using Nix to set up their 50 language environments, and they made a public bet on the tech. And then I saw at the start of the pandemic, Shopify were switching all the development setup to it. It's hard to say Nix is on its hype cycle, given how long it's been around, but there certainly has been a shift in usage over the past few years. And with this hype I'm about to tell you, comes a big fat disclaimer. Nix is super complex. You should not trust anyone who says otherwise. It has a fairly steep learning curve to truly master, and the developer experience is still actively being worked on. So, what is Nix? It's a package manager and an operating system and a language, and they really could have spent more time on naming, but alas. We are going to focus on the package manager bit. I'm always wary of hype, so I'm going to try and explain how I sold it to myself by starting with what it promises, why the authors felt it needed to exist, and then cover its core working mechanics. Hopefully without sounding like a fanboy. The fact is, it's a tool that let us get back to building our app, which is what we want to do. We're not here to care about Nix, we're here to get our job done without wanting to poke our own eyes out. So, without further ado, Nix's first release was in 2003, followed by this paper, which got released in 2004. Honestly, this came as quite a shock to me when researching, as I've only been reading about it since 2018. And I was at school in 2003 when this came out. The paper itself is a fantastic, approachable read. I'd recommend anyone to get a deeper dive on the why and how Nix exists. Notably, it calls the act of transferring an app to different environments a deceivingly hard problem. And I think we as Python developers can agree, given what we've been through. So what does it promise? Reproducible builds. Given the same input, the working output should be the same on another machine. Now, you might be thinking here, this is what Docker offers, but Docker offers runtime reproducibility and not build time. When you build an image with Docker, the resulting image is portable and obviously will reproduce because of that. If you run the build again, say a day later, on the same Docker file, the resulting image may differ. This might be what you want, but it is not reproducibility, and that's the fact with Docker. So, Nix is declarative, in that you describe aspects to construct the environment you want. Again, this is slightly different to Docker, because with Docker files you build your world procedurally, line by line, in the Docker file, and anything could happen on those lines. It promises us an explicit dependency graph. So Nix's belief is that every piece of software on your machine implicitly relies on each other and on the hardware it was built with, and the platform too. At its core, Nix is a graph generator to make all those links explicit and therefore aid in portability. If the promise, skip, next one. So another thing it promises is cross-platform builds. So it has full support for Linux and macOS, which is a rare thing. And it also supports Windows if you're using the Windows subsystem for Linux. And then you use it via Ubuntu instead. So this ticked all of our boxes, because these are the 3 operating systems we work with on a daily basis. Okay, cool. But how does it do that? So if you're like me, promises are not enough. Until I can get a true understanding of how something works, I leave it in the hype basket. So I'm going to try and explain the core blocks in a way which gives you just enough to get it, but doesn't make you hate me. So next up, we have the first building block of Nix is the store. So after you install Nix, you'll be left with this directory on your machine. This is where Nix keeps its stuff. You can think of it like a massive cupboard with 100 drawers. If you take a look inside it, you'll see a mixture of directories and files all appended with a hash. The hash is very important, but just remember it exists for now. What you are looking at is Nix file system-based graph database. So each entry in this directory, whether it be a directory or a file, is a node in that graph. And the relationships between them are the edges of that graph. So some facts about the store that will help you understand how it acts. So only Nix can write to the store. It is a special zone, untouchable by anything else. Once a node is written, it's immutable, so it can never change. The node will have the same name on any machine that it's built on. You just have to trust me for that for now. And if you want to see the Nix dependency graph in action, you can run this nixstore command, passing it any node, and then pipe the contents the graph is, which will generate this hideous-looking beast. As you can see, I've used my active Python node here, and it depends on OpenSSL, which in turn relies on Apple's Core Foundation, which in turn relies on libObjective-C. None of these concepts are new, it's just it's system-level software. We haven't had a good story for that pretty much ever. Cool. So, how does Nix know what to write to the store? Earlier we said one of the rules of the store was that only Nix can write to the store. And the answer to that is derivations, which is a super scary word. They're a scary name for a file which exists as a node in the store itself. And the responsibility of that file is an instruction set on how and where to build one or more other nodes. These are the DRV files you see before you, and their contents look like this. Now, thankfully, you don't actually need to read this. This is a JSON representation rather than the actual plain text DRV format, but it gives an understanding of the data structure within. It's a simple key value JSON-like object. The derivations contain all the Nix storage edges, the paths, all the dependencies of the package in question. And the hash of the contents of the file end up dictating the path the derivation is stored at in the Nix store we showed earlier. This is important because if a dependency the package relies on changes, this would result in a new derivation. As I said, they're completely immutable. So, what kind of stuff actually exists in this file? It literally defines how to build the package from source. That's a key part of Nix, is that it's a flexible package manner. So while it has a binary object hash that you can use, everything can be built from source because you have everything you need to do that. So if we look through the arguments, the platform is what operating system is on, macOS, Linux. The input DRVs, this is the other derivations that we depend on and that would be needed to do the build. The input sources is the other already built nodes that we depend on. The builder is what program runs the build. Is it bash, is it GCC, what is it? Args and env are arguments and environment variables for the build. And the outputs is like which files get output into the Nix store due to running this build. Okay, cool. But what makes the derivations? And this is where it gets a little bit more complex. The answer is Nix, the language itself. This is probably the most controversial part of Nix, or at least the part I see questioned the most. So why does Nix need its own language? Why can't I just use YAML? The answer is because Nix's goals are unique amongst all package managers. Nix the language is both incredibly helpful to learn, but also the most useless for any other purpose. But that uselessness is entirely deliberate. It is entirely deliberate. So it has two standout features which make it safe and good for this use case. Number one is that the entire language is lazily evaluated. So I think a lot of you will be aware of Django's lazy string translation or the lazy URL lookup. And what the idea here is exactly the same, except it's applied to the entire language. Anything you write is only evaluated when it is actually needed. And therefore, when you're dealing with massive graphs of data that depend on certain scenarios, it speeds everything up. And the second most important feature is that it's side effect free. And by side effects, I mean any input output. So no network, no like console log or anything like that. There is a bit of debug output, but there's no disk access and no user input. And that's why it's useless language for other use cases. So, there is one exception to the no side effects rule. And in understanding what it is, you'll understand the whole purpose of the language. So when you call the derivation function, this derivation function with parameters, Nix writes the derivation to the store. The sole purpose of the Nix language is to create derivations. And so it's these well, you write derivations with the Nix language as part of working out what the dependencies are for your given package at any given time. And the final building block, because everything I've said is useless if Nix cannot ensure the various builds only pull from the store, is sandboxing. And it does this in two ways: by providing patch versions of compilers and linkers that don't look in the normal locations, and secondly, more importantly, by building each derivation within a sandbox that denies access to anything it isn't supposed to get its grubby hands on. And this leads into how we take advantage of it for developer environments. It all starts with a little tool that ships with Nix called Nix Shell. And when you run it, it looks for a file in the current directory called shell.nix. And in that file, there should be a derivation, a defined definition, and the output, and basically what it does is it runs that derivation, puts everything it needs into the Nix store, creates a bash subshell, relinks everything so that that subshell only has access to what it actually should have, and from then onwards, your shell is fine. So if any of you used to use make virtual env or any of the virtual env wrapper stuff, you know about shims and you know about how they change the shell paths to make sure we're working in an isolated environment. This isn't much different. All your binaries just end up pointing direct to the Nix store. And so you may be asking, do I have to build everything from source myself? No. Because of the immutability and because of all the metadata which goes into creating a unique Nix node, that string can be treated as safe to cache once that node is built. And so that's where Nix packages comes in. It's the official package repository for the Nix ecosystem, and it's basically a giant repo on GitHub full of derivations that other people have supplied. One thing, so Nix packages has a giant cache of everything you need. So you end up just downloading from the cache when installing because they have a lot of machines running all these derivations and creating all different builds for all different platforms. So yeah, you don't have to build everything from source. Cool. Awesome. So this gets us to our little shell Nix, which sits in our platform repository. And I'm going to walk over here a little bit so I can see it. I'm going to talk through what this is, what the various parts do, but you don't really need to know about like the Nix language, which this is. So at the top, you have the imports and aliases. So that first line, what it's doing is it says, get the Nix package tarball from GitHub at this exact commit. And this exact commit maps to a channel, which are basically like branches. So they have one for stable, unstable, and then various operating system releases. The following three lines are imports, and then the packages make shell function. That's our call, which creates the derivation for us. So then the native build inputs attribute, we just list what we want. And And as you can see, we set up our Python, poetry, pre-commit, Node.js, Yarn, everything is defined in there. And then what we also do is we use it as a base layer for still using Yarn and poetry. We haven't gone full Nix. You can go full Nix if you want, but it's a bit too much for now. We just wanted a base layer that we could actually always run poetry and never get a failure due to something not being on the system or whatever. And so for each package that needs custom stuff, we just include the package there. And as you can see at the bottom, there's a little exception for Darwin systems, which is macOS. Yeah, so you need Xcode build, and for some reason Node Canvas doesn't build unless you have that frameworks Cortex thing. And then at the bottom, you have the shell hook, which is it's basically a bash shell script which you can execute on entering into the Nix shell. So one problem with this setup, which worked flawlessly out of the box, which is really handy for us, one problem we did have early on is a bit of a faff having to constantly remember to be inside the Nix shell when you enter a directory. So luckily, Derivations.net has a native integration that makes this really easy and solves two problems in one go. One, you get the automatic Nix shell instantiation on entering a directory. And two, you get to use whatever shell you want with your own prompt rather than using Nix as a bash subshell. And so what does it look like for us? We enter the directory. It's a video, classic. Oh, it is running, cool. So yeah, so you enter the directory, and boom, you get our little ASCII art thing. You get to, we output the exact Python version you're on, the exact Node version you're on. We also have a little shim to basically say if your Python dependencies are up to date with the poetry install, and same again for Yarn. And it's just been super helpful to us. Another issue we had is that we still needed to run the services via Docker. Remember, they were fine. So we left them in Docker. So without some form of solution, we'd now be opening 3 terminal windows to do local development: the back end, the front end, and Docker-compose itself. We'd actually had this problem of having no shared task language amongst the team for a while. So we decided to go looking for a modern Makefile alternative and came across Taskfile, which is written in Golang. It's fantastic. It's a YAML-based definition. More YAML, I know, but it's good. You can run tasks in parallel. Tasks can have dependencies of other tasks. You can pass arguments straight from the command line through down into the task below. It's just a really nice API for getting stuff done. And this is what it looks like for us when we just run task. It gives us a nice documentation of all the scripts you can run on the repo, basically. And for instance, once you're inside the shell, you can simply run task up to bring the entire stack up. It's just one command. And obviously, by entering the directory, Nix has set up all its stuff and installed everything for you. So to bring up our stack, it can just be the case of checking out the repo, installing Nix, going into the directory, and then running that command, which is super great. So the results, I'm getting close to the end. Huge speed ups across the board. Way more than 50% we were hoping for. Run server reload down to 3 to 5 seconds. I was speaking with the Colo peeps outside about getting this down further because I still think it's quite slow, to be honest, for a large project. Needless to say, it was a massive success. But the larger success was really discovering Nix. And that brings me on to what's next. So we could go full Nix if we wanted to, and by full Nix I mean that we would also declare all of our Python dependencies and all of our JavaScript dependencies within Nix itself. There are projects to help you do this. One of them is called Poetry to Nix, and that can take a poetry file and basically convert it into a Nix derivation. We tried that. We used some weird packages, and there's a lot of little hacks that Poetry to Nix do because the Python ecosystem, like for example, if you install I don't know, LXML from source, there's nothing in the Python ecosystem that tells you it needs specific things of GCC and other compilers on your system. So yeah, so it's one for us to look at. More interestingly for me, we still deploy to Heroku the old school way with build packs, but we're looking to move away. And that will inevitably mean deploying Docker containers. So Nix is amazing at creating Docker images. What better way to build them in a reproducible fashion? There's literally a function which is a couple of lines, and you'll have from any given derivation, you'll have your image, and you'll be ready to go. And Railway, they're a Heroku competitor, have just launched nixpacks.com. And so if you kind of want to skip a lot of the inner bits of Nix and want to just get something running in a bunch of given languages, go and have a look at that. And last slide. So the future, what does the future hold? I think I'm going to have to skip this because I'm running out of time, but if you want to talk to me later about why I think the future of local development actually is in the cloud, then do catch me afterwards. Having said all this, it's a strange point to end on, given I've just told you about Nix. The thing is, Nix is going to be useful in the cloud anyway. A lot of how those services work, like Gitpod, Octeto, and some other ones, they basically run Docker images. And so what are you going to want? You're going to want reproducible Docker images. And there you go. Thanks. Okay.